Gas laws and their fundamentals are critical to understand respiratory physiology. In this video, I'm going to tell you what is solubility coefficient and what are the factors affecting solubility of gas in liquid. Hey everyone, welcome back to HM Learnings. I am Harshita, the creator of HM Learnings, where students come to clear their concept and to get the study material. Make sure you subscribe my channel. So today we are back with the next video on the respiratory physiology, that is part 2 of physics of gas. So in the previous video we have talked about how oxygen and carbon dioxide dissolves in water. Then we have also seen what is pressure of gas, what is Dalton's law, what is partial pressure, what is ideal gas law, and then we have seen the Henry's law. So we have already discussed what is Henry's law and we have ended the previous video on the topic of solubility coefficient. So before starting today's video on solubility coefficient, we are going to take a quick recap on what is Henry's law. So Henry's law is basically defining that what will be the volume of a gas dissolved in a liquid. What is like, how can you determine that what will be the volume of gas what will be the volume of gas which will be dissolved in liquid? Okay, so that could be understand by here. You can see that basically arterial plasma, the liquid is being, instead of liquid we will say that there is arterial plasma, and instead of gas we will say oxygen. So if you're taking a beaker which is filled up with the arterial plasma, this is arterial plasma, and you're having oxygen, so here the partial pressure of oxygen is 100 mmHg. So basically you have exposed the arterial plasma to the atmosphere which is having a PO2 of 100 mmHg, and then there will be a diffusion of oxygen molecules, and ultimately there will be an equilibrium of the oxygen between the gaseous phase and the liquid phase. So after achieving the equilibrium, what will be the volume of oxygen which will be dissolved in 100 ml of arterial blood is something which is defined by the it is something which is defined by the Henry's law, and it is directly proportional to the partial pressure of oxygen. So that means more the partial pressure of oxygen in the atmosphere, more will be the amount of oxygen dissolved in the arterial plasma. So here this constant, or not the constant, but this proportionality is being replaced by a constant which is called as a solubility coefficient, which is different for different gases. Since we are talking about the oxygen, it will be solubility coefficient of oxygen. So we can say that the amount of oxygen dissolved in 100 ml of plasma will be equal to the product of solubility coefficient of oxygen into the partial pressure of oxygen in the gaseous phase, and this is Henry's law. Now we are going to talk about what is solubility coefficient. So to understand solubility coefficient, let us take the help of this example only. So if I can write solubility coefficient is equal to volume of oxygen dissolved in 100 ml of plasma divided by the partial pressure of oxygen in the gaseous phase, which is in the mmHg. Okay, so this is what is the solubility coefficient, which is equal to, the solubility coefficient of oxygen will be equal to the volume of oxygen in ml dissolved in 100 ml of plasma when that arterial sample is equilibrated with the atmosphere which is having a PO2 of 1 mmHg. So that means I could write that, suppose we can see the x ml of oxygen is dissolved in 100 ml of blood, or per 100 ml of blood, or per unit ml of arterial plasma per mmHg of the PO2 in the gaseous phase. This is how you are going to write the solubility coefficient. So the solubility coefficient of oxygen is equal to 0.003 ml of oxygen dissolved in 100 ml of plasma when the atmospheric pH, when the atmospheric PO2 is 1 mmHg. So if there is 1 mmHg of PO2 in the atmosphere, the amount of oxygen dissolved in the arterial plasma will be equal to 0.003 ml in 100 ml of the plasma. So that means in 1 ml of plasma you are going to have how much oxygen dissolved? 0.003 divided by 100 will be your per unit ml of per unit ml of plasma is containing this much amount of the oxygen. So this is what is the solubility coefficient. So here I can draw the diagram again, that you are having an arterial plasma. In the arterial plasma, you are this arterial plasma is exposed to PO2 of 1 mmHg, and in response to that, how much VO2 you can found in 100 ml of the blood is going to be your solubility coefficient of oxygen. So this solubility coefficient of oxygen is different for different gases, and you can say here that the solubility coefficient is defined or determined by the defined or determined by the nature of the solute and solvent. Okay, so here we can see what is the next point. So oxygen dissolved in liquid phase is direct. This is what the Henry's law, which we have seen. Then the solubility coefficient is defined, is denoted as S or K, which is the volume of gas dissolved in per unit volume of liquid per unit pressure of gas in gaseous phase at constant temperature and pressure. So there is no change in the temperature and the pressure conditions, and that is how you define you write the solubility coefficient. Now solubility coefficient is being, as I said, it is different for different gases. Actually it is determined, actually depends upon the solute in solvent. So how does the solute is going to interact with the solvent will determine the solubility of a solute in a solvent, as we have already discussed in the previous video, which is like dissolves in like, that is polar is going to dissolve in polar and non-polar is going to dissolve in the non-polar. So that means there is solute and solvent interaction, which is going to determine how much solute is going to dissolve in this particular solvent. So similarly, your nature of solute and solvent will decide how much will be the solubility coefficient. More the solubility coefficient is there, more the gas will be soluble in that particular solvent. So you see in this diagram, this is in this table, this is showing the solubility coefficient of gases at the temperature, at the body temperature, since we are saying that it is going to happen at a constant temperature and pressure, and the atmospheric pressure is 760 mmHg in water. Okay, so they are talking about how much these gases are going to dissolve in water at 760 mmHg. So they are getting the oxygen solubility coefficient as 0.024, which can also be written as 0.003. Major of the textbooks are writing it as 0.003. Carbon dioxide is 0.06, and then other gases such as carbon monoxide, nitrogen and helium. So you see it is different for different gases. So in all these cases you see that the solvent is the same. Solvent is the arterial plasma, which is consisting of water. So in all these the solvent is the same. That means the only difference, the only thing which is bringing the difference in the solubility coefficient is the solute, that is the particular gas. So the way the oxygen is interacting with the water and the way the carbon dioxide is interacting with the water is different. So if the water is more, if some molecule, if some gas is the gas molecules are more attracted by water, that means the water can hold more water molecules of that particular gas. Or let's understand one more concept which we forget to discuss in Henry's law. So as we have discussed the Henry's law that PO2 is 100 mmHg, and therefore the amount of oxygen dissolved will be directly proportional to the PO2 in the gaseous form. That is what is the Henry's law, and then it is replaced by the solubility coefficient of the oxygen, and then you can get the PO2 in 100 ml of the arterial blood. Now basically we can say that after getting equilibrating with the gaseous phase, even when the oxygen dissolves in the water or in the plasma, it's still exerting the partial pressure. It is still having the pressure which is acting against the wall, okay, against the blood vessels. So how much is the pressure which is going to be exerted by the dissolved oxygen in the plasma? That will be still equal to PO2 of 100 mmHg. So if we are saying that we are having an arterial plasma, in that arterial plasma the VO2 is about, if we calculate here, solubility coefficient is 0.0 0.03 into 100 mmHg. So you get 0. Uh, 0.3 ml of oxygen dissolved in 100 ml of arterial blood at 100 mmHg of partial pressure. Okay, so of PO2, 100 mmHg of PO2, around 0.3 ml is being dissolved in 100 ml of arterial blood. So the VO2 of this, the amount of oxygen dissolved in 100 ml of arterial blood is equal to 0.3 ml. But what does this 0.3 ml is contributing in terms of the pressure exerting by that in the solution form against the vessel is still the 100 mmHg. So this arterial blood is containing 0.3 ml of dissolved oxygen, and that oxygen molecules are exerting the partial pressure of around 100 mmHg. Similarly, if we say that PCO2 is exerting is having a partial pressure of 40 mmHg in the arterial blood, that means that this amount of blood, this 100 ml of blood, is exerting 100 mmHg of the partial pressure of oxygen, and also it is having the 40 mmHg partial pressure of carbon dioxide, which is exerted by the carbon dioxide molecules against the wall. So they are, even in the dissolved form, they are going to exert the partial pressure, and that pressure will be equal to the pressure to the pressure in the gaseous stage to which it is equilibrated. So you are equilibrating the arterial pressure with the atmosphere or with the alveoli, which is having PO2 of 100 mmHg. So that means your blood plasma is also going to exert a partial pressure of PO2. Similarly, for the carbon dioxide, it will exert a PCO2 of 40 mmHg. So now you can see that there is a difference in the solubility coefficient of the oxygen and carbon dioxide. So if by using Henry's law, you calculate the amount of oxygen dissolved in the 100 ml of arterial blood at 100 mmHg of PO2 of the oxygen, you will get 0.3 ml of oxygen in 100 ml of arterial blood at PO2 of 100 mmHg. Okay, so if you increase the PO2, what will happen? The VO2 will also going to be increased. If you talk about the volume of carbon dioxide dissolved in 100 ml of blood, you multiply the solubility coefficient of carbon dioxide, which is 0.06, into 40. 40 mmHg is a PCO2 in the arterial blood, and that is going to come around 2.4 ml of carbon dioxide in 100 ml of arterial blood at PCO2 of 40 mmHg. So here you see that, as we have seen in the Henry's law, which says that more the partial pressure of a gas, more will be the solubility of that gas in the liquid phase. So if you see that VO2 of 100 mmHg and PCO2 of 40 mmHg, which one is higher? The PO2 of 100 mmHg is higher, but still only the 0.3 ml of oxygen is dissolved in the arterial blood, whereas with a lesser partial pressure, there is more amount of the carbon dioxide which is dissolved in the same amount of the blood. The difference which is there is not because of the partial pressure, but it is because of the solubility coefficient. So it is the way of interaction between the CO2 and the water, which is different from the way of interaction between oxygen and water molecules. So CO2 is something which is more soluble. The molecules of CO2 are attracted more by the water, and hence the same amount of the water molecule can hold more CO2 closer with each other, and because these molecules are closer with each other, they are going to exert the lesser partial pressure or against the walls. And this is in the case of the oxygen, the lesser molecules are going to be holded by the water molecules because it is more repulsion as compared to CO2, and as a result, because the oxygen molecules are repelled, they are going to exert the more partial pressure against the wall. So it's not only the partial pressure which is defining the solubility of how much volume of the gas is going to be dissolved in a liquid. It is also going to be your solubility coefficient, which is depending upon the nature of the gas and the solvent. Okay, So this is important, and that is how, because the CO2 is different. Now how does the CO2 interaction with water is different from the O2 interaction with the water? Because of the structure of the molecules. O2 structure is different from the CO2. So that is how your CO2 is around 20 to 23 times more soluble in the arterial plasma than the O2. Okay. So now we have talked about the solubility coefficient and also about the Henry's law. So you see that solubility coefficient, if you multiply the solubility coefficient with the partial pressure, you get the solubility of you get the volume of that gas in a liquid phase. So solubility coefficient is basically the amount of that gas dissolved in per unit ml or 100 ml of the liquid at 1 mmHg of that partial pressure of that gas in the gaseous phase. So if you multiply it with the partial pressure of that gas in the gaseous phase, you get the volume dissolved of that gas in the liquid phase. Okay. So I hope I am clear with this, that carbon dioxide is 20 to 23 times more soluble, because carbon dioxide molecules are more attracted to water molecules, and as a result, even though the partial pressure, even though the partial pressure in the atmosphere of carbon dioxide is lesser, in the environment, the partial pressure of oxygen and carbon dioxide is different. So partial pressure of oxygen in the environment is around 150 mmHg, whereas for the CO2 it is only 0.3 mmHg. But still, in the blood you can see that there is more amount of the carbon dioxide soluble than the oxygen, and the answer is because of the solubility coefficient, because of the way they are interacting with the water molecules. Now, what are the factors which are determining the solubility of gas and liquid? This we already discussed. This is just to put all these things at the same place. Nature of solute and solvent, which is explained by the solubility coefficient. Then pressure. If you increase the pressure, then we are not talking about two different gases. In the same gas, the solubility coefficient is going to be the constant only. Then if you increase the pressure, then this amount of oxygen dissolved, amount of any gas dissolved in liquid is going to be increased at a constant temperature. So remember, if you're considering one factor, you have to make the other factors constant, so that you can talk about the effect of only one factor at a time. Then temperature, this we haven't discussed till now. If there is increase in the temperature, what happens? The molecules are going to move at a greater speed. As a result, the solubility is going to be decreased. Okay, so there is decrease the solubility of gas and liquid when there is increase in temperature. This is called Le-Chatelier's principle. So we have came end to this video. These are the two references you can look upon. They have written very well these concepts. So if you like this video, please like, share and subscribe the channel. Till then, keep learning.